Tonight, we're going to take a slow journey through some of the most puzzling discoveries astronomers have ever made. Out there in the vast darkness of space, scientists have found signals, stars, and cosmic structures that don't quite behave the way we expect. Not in dramatic or explosive ways, but in quiet, subtle ways that leave researchers wondering whether something important is missing from our understanding of the universe. For the most part, the cosmos follows clear and predictable rules. Gravity pulls matter together, stars burn their fuel for billions of years, and galaxies arrange themselves in patterns shaped by physics that astronomers have studied for decades. When we observe distant objects through telescopes, we usually find that they behave more or less the way our models predict. But every so often, something appears that doesn't fit neatly into those models, a signal that appears once and never returns. A star that dims in ways that planets cannot explain. A structure so large that it challenges our understanding of how matter is distributed across the universe. These discoveries are rare, but they are real. They have been detected by powerful telescopes, analyzed by researchers, and discussed in scientific journals. Some may eventually turn out to have simple explanations that we just haven't discovered yet, while others might reveal entirely new processes at work in the universe. In this video, we'll slowly explore 10 of these unusual discoveries. Each one is a genuine scientific mystery, not speculation, not science fiction, but observations that still leave astronomers with unanswered questions. And perhaps the most famous of these mysteries began with a single, brief signal detected almost half a century ago. On August 15th, 1977, a radio telescope in Ohio picked up something unexpected. At the time, researchers at Ohio State University were operating a large radio telescope known as the Big Ear as part of the search for extraterrestrial intelligence, or SETI. Its purpose was to scan the sky and listen for radio signals that might suggest the presence of intelligent life somewhere in the galaxy. Day after day, the telescope recorded radio emissions from space, most of which were ordinary background noise produced by natural cosmic sources such as stars, galaxies, and clouds of gas. The data was printed onto long sheets of paper filled with numbers that represented signal strength, and usually nothing remarkable appeared in those printouts. But on that August day in 1977, researcher Jerry Amon noticed something unusual while reviewing the telescope's data. In the middle of the numbers was a signal far stronger than anything around it. The burst lasted for 72 seconds, and during that short time, it was about 30 times stronger than the surrounding background noise. It appeared to come from a region of the sky near the constellation Sagittarius. Surprised by what he saw, Amon circled the numbers on the printout and wrote a single word in the margin: "Wow." That simple note gave the signal its famous name, the WOW signal. One of the most intriguing aspects of the signal was its frequency, which appeared close to 1,420 megahertz, a frequency naturally associated with hydrogen atoms, the most common element in the universe. Because of this, scientists have long suggested that if an intelligent civilization wanted to send a recognizable signal across the cosmos, it might choose a hydrogen-related frequency as a kind of universal marker. The signal was also unusually narrow in frequency, something that is more typical of artificial transmissions than natural cosmic radio sources. Yet despite decades of searching, astronomers have never detected the signal again. Telescopes have repeatedly scanned the same region of space with instruments far more sensitive than the original Big Ear. But the mysterious burst has never returned. Some scientists have proposed natural explanations, including the possibility that the signal came from a passing comet releasing hydrogen gas, but the details do not perfectly match the observations. Others have suggested interference from Earth, although the telescope was designed to filter out many types of terrestrial signals, and the source appeared fixed in the sky. As a result, the true origin of the WOW signal remains unknown. It lasted just over a minute in the summer of 1977, appeared suddenly in a quiet stream of data, and then disappeared forever, leaving behind one of the most famous unsolved puzzles in the history of astronomy. Now let's move to another mystery that has puzzled astronomers for more than a decade. About 1,460 light-years away from Earth, in the constellation Cygnus, sits a star that appears perfectly ordinary at first glance. Its official name is KIC 8462852, though most astronomers know it as Tabby's star, named after astrophysicist Tabitha Boyajian, who helped lead the research that brought this strange object to worldwide attention. On paper, there is nothing remarkable about the star itself. It's slightly larger and hotter than our Sun, but otherwise it looks like a fairly typical main sequence star. If astronomers had simply catalogued its temperature, brightness, and distance, it likely would have gone unnoticed among the hundreds of billions of other stars in our galaxy. But in 2011, while scientists were examining data from NASA's Kepler Space Telescope, they noticed something extremely unusual about this star's brightness. Kepler was designed to search for planets around other stars by watching for tiny dips in starlight that occur when a planet passes in front of its host star. When a planet transits its star, the light dims slightly in a regular and predictable pattern. Earth, for example, would dim the Sun's light by less than 1/100% if observed from another solar system. Even a large planet like Jupiter would only block about 1% of the Sun's light. These dimming events are small, precise, and repeat at regular intervals as the planet continues its orbit. But Tabby's star wasn't behaving that way at all. Instead of small, predictable dips, the star's brightness dropped dramatically and irregularly. In some observations, the light dimmed by as much as 15%, and in others the dimming reached nearly 22%. That is far too large to be caused by a planet. To block that much light, something enormous would need to pass in front of the star, something comparable in size to the star itself. Even more puzzling, the dimming events did not follow a simple or repeating pattern. Sometimes the brightness would drop suddenly and then slowly recover. Other times the dimming was gradual and uneven. There was no clear rhythm to it, and nothing else in the Kepler data behaved in quite the same way. When the discovery became widely known, it triggered a wave of scientific curiosity and speculation. Astronomers began searching for possible explanations that could account for such unusual behavior. One of the earliest ideas was that a large swarm of comets might be orbiting the star. If hundreds or even thousands of comets passed in front of the star at different times, their dusty tails could block varying amounts of light and create irregular dimming patterns. While this idea seemed plausible at first, it raised several problems. A comet swarm large enough to block 20% of a star's light would have to be enormous, and astronomers struggled to explain where such a massive collection of comets might have come from. Another possibility was that a recent planetary collision had produced a large cloud of debris orbiting the star. If two planets or large bodies smashed together, the resulting fragments could scatter around the system and temporarily block starlight as they moved through our line of sight. However, collisions like this should produce large amounts of warm dust which would glow in infrared light. Observations of Tabby's star did not show the level of infrared radiation that astronomers expected from such a debris cloud. The star continued to resist simple explanations. For a brief period, one more exotic idea even entered the conversation: the possibility of a Dyson swarm, a hypothetical collection of energy-collecting structures built around a star by an advanced civilization. Such structures could, in theory, block large and irregular amounts of starlight as they orbited. Most scientists were careful to treat this idea as extremely unlikely, but the fact that it had to be considered at all illustrates how unusual the observations were. In recent years, further observations across different wavelengths have suggested that fine dust particles may be responsible for at least some of the dimming events. The dust appears to scatter blue light more strongly than red light, which is consistent with certain measurements of the star's brightness changes. Even so, important questions remain unanswered. Astronomers still do not know exactly where the dust is coming from, how it formed, or why the dimming patterns remain so irregular. After more than a decade of study, Tabby's star continues to behave in ways that astronomers have rarely, if ever, seen before. Among the hundreds of billions of stars in the Milky Way, it remains one of the most puzzling objects in the sky. In 2019, astronomers studying the radio sky stumbled upon something they had never seen before. While analyzing observations from a powerful radio telescope in Australia, researchers noticed several enormous circular structures that appeared faintly in their data. At first, the discovery seemed almost too perfect to be real. The shapes were nearly flawless rings, glowing softly in radio wavelengths and stretching across enormous distances in space. The team wondered if the circles were simply artifacts created by the telescope or errors in the data processing. In astronomy, perfect geometric shapes often raise suspicion because nature rarely produces them so cleanly. But as the scientists continued examining the observations, it became clear that the circles were real. These objects became known as odd radio circles, or simply ORCs, a name that perfectly captured both their appearance and the mystery surrounding them. Unlike galaxies or nebulae that can easily be seen with optical telescopes, ORCs appear only in radio wavelengths, meaning they are invisible to the human eye. When astronomers observe the sky using radio telescopes, they detect energy emitted by cosmic particles moving at high speeds, often associated with powerful magnetic fields or energetic events in distant galaxies. The first ORCs were detected using the Australian Square Kilometre Array Pathfinder, a highly sensitive radio telescope designed to map the universe in unprecedented detail. When scientists looked at the images produced by the telescope, they noticed several enormous rings floating quietly in the data. Each ring was vast, sometimes hundreds of thousands, or even more than 1 million light-years across. That makes them many times larger than the Milky Way galaxy itself. Even more intriguing was the fact that many of these rings appeared to have a galaxy sitting almost exactly at their center. Yet the galaxies themselves looked ordinary when observed in visible light. They showed no obvious signs of the extreme activity that might normally produce such gigantic structures. As astronomers began studying these objects more closely, they quickly realized that ORCs did not resemble any known cosmic phenomenon. They were too large to be supernova remnants, which are expanding shells of gas created when stars explode. Supernova remnants are typically only a few dozen light-years across, while ORCs are hundreds of thousands of light-years wide. They were also far too large and distant to be planetary nebulae, which are clouds of gas released by dying stars. Another possibility was that they might be related to radio galaxies, where supermassive black holes at the centers of galaxies launch powerful jets of particles that create enormous lobes of radio emission. But when astronomers studied the galaxies located at the centers of these rings, they did not see the kind of active black holes that normally produce such radio structures. The galaxies appeared relatively quiet. Several theories have been proposed to explain the existence of ORCs. One idea suggests that they may be shock waves from massive explosions that occurred millions of years ago in distant galaxies. If a galaxy experienced a powerful burst of star formation or a sudden outflow from its central black hole, it could potentially send a wave of energetic particles expanding outward into intergalactic space. Over vast periods of time, such an expanding shock wave might create a spherical shell that appears as a ring when viewed from Earth. Another hypothesis is that ORCs could be connected to collisions between galaxies, where enormous gravitational interactions trigger waves of energy moving outward through the surrounding gas. However, galaxy mergers are relatively common events in the universe, while ORCs appear to be extremely rare. As of today, astronomers have identified only a small number of these objects, making them difficult to study in detail. Their rarity is part of what makes them so fascinating. It's possible that ORCs have existed all along, but our telescopes simply weren't sensitive enough to detect them until recently. Modern radio observatories are revealing new aspects of the universe that were completely invisible just a few decades ago. For now, odd radio circles remain one of the newest and most puzzling discoveries in modern astronomy. They are enormous, mysterious rings drifting silently through deep space, waiting for scientists to uncover the events that created them. On the largest scales imaginable, the universe appears surprisingly orderly. Galaxies are not scattered randomly through space. Instead, they form a vast network, often called the cosmic web, where enormous filaments of galaxies stretch across the universe, while vast empty regions known as voids lie between them. When astronomers map these structures, they see clusters, walls, and filaments that extend for hundreds of millions of light-years. According to current cosmological theory, however, there is a limit to how large such structures should be able to grow. This idea comes from something known as the cosmological principle, one of the fundamental assumptions behind modern cosmology. The principle states that when you observe the universe on extremely large scales, matter should be distributed roughly evenly in all directions. In other words, while galaxies may clump together locally, the universe should look statistically similar, no matter where you look if you zoom out far enough. For decades, astronomical observations have largely supported this idea, but in recent years, two enormous discoveries have begun to challenge it. The first of these structures is known as the Giant Arc, discovered by cosmologist Alexia Lopez while studying the distribution of distant galaxies. The Giant Arc is not a single object, but a vast arrangement of galaxy clusters stretching across an astonishing 3.3 billion light-years. To put that into perspective, light itself takes 3.3 billion years to travel from one end of the structure to the other. That makes it one of the largest known structures in the observable universe. The arc appears as a curved line of galaxies forming a gigantic arc-shaped pattern in the sky. It lies roughly 9 billion light-years away from Earth, meaning we see it as it existed when the universe was significantly younger than it is today. Even more surprising is that this structure appears far larger than what theoretical models predict should be possible. Based on current cosmological simulations, structures should rarely exceed about 1.2 billion light-years in size. The Giant Arc is nearly 3 times that limit. Not long after the discovery of the Giant Arc, researchers identified another massive structure in roughly the same region of space. This second structure is known as the Big Ring. As the name suggests, it forms a gigantic circular arrangement of galaxies with a diameter of about 1.3 billion light-years. Like the giant arc, the Big Ring is located approximately 9 billion light-years away, suggesting that both structures may be part of the same large-scale region of the universe. The presence of two enormous formations so close to each other raises intriguing questions. If these structures are truly connected, they may represent an even larger cosmic feature that astronomers do not yet fully understand. What makes both discoveries so fascinating is how they challenge expectations about how matter organizes itself across cosmic distances. In theory, gravity has only had a limited amount of time since the Big Bang to pull galaxies together into clusters and filaments. Structures on the scale of billions of light-years push the limits of how quickly gravity should be able to assemble matter into such patterns. Some scientists have suggested that the giant arc and the Big Ring might simply be statistical coincidences, patterns that appear meaningful when we look at large datasets of galaxies, even though they are not physically connected structures. When humans look at maps of the sky, our brains naturally try to identify shapes and patterns, sometimes seeing connections where none truly exist. However, statistical analysis performed by researchers indicates that the probability of the giant arc forming purely by chance is relatively low. Another possibility is that our understanding of large-scale structure formation may need refinement. The universe might be capable of producing larger structures than current models predict, especially if certain conditions in the early universe allowed matter to clump together more efficiently. Some more speculative ideas involve exotic possibilities, such as cosmic strings, hypothetical defects in space-time that may have formed shortly after the Big Bang. If such structures exist, they could potentially guide the formation of galaxies along enormous lines or loops across the cosmos. At the moment, however, there is no direct evidence that cosmic strings are real. As with many mysteries in astronomy, more observations will be needed before scientists can determine whether the giant arc and the Big Ring truly represent violations of the cosmological principle or simply unusual patterns within the cosmic web. What is clear is that the universe continues to surprise us. Even on the largest scales we can observe, the cosmos may still hold structures far bigger and more complex than we once imagined. If you look at a detailed map of the universe, you'll notice that galaxies are not spread out evenly through space. Instead, they form long filaments and clusters that weave together into an enormous structure known as the cosmic web. Between these filaments lie vast regions where very few galaxies exist. These regions are called cosmic voids, and they are a natural consequence of how gravity shapes the universe over billions of years. In the early universe, matter was distributed almost uniformly after the Big Bang, but tiny fluctuations in density meant that some regions contained slightly more matter than others. Over time, gravity amplified these differences. Areas with a bit more matter began pulling in additional material, eventually forming galaxies and galaxy clusters. Meanwhile, the regions with slightly less matter slowly lost material to their surroundings, becoming emptier and emptier as the universe evolved. As a result, the cosmic web formed, dense filaments of galaxies surrounding enormous bubbles of relatively empty space. Most cosmic voids are already immense, often stretching tens of millions of light-years across. But one of them stands out as particularly extreme. In the early 1980s, astronomers studying the distribution of galaxies discovered a vast region in the direction of the constellation Boötes that appeared unusually empty. This region became known as the Boötes Void, and it quickly earned a reputation as one of the most mysterious large-scale structures in the universe. The Boater's Void spans roughly 330 million light-years in diameter. To put that into perspective, the Milky Way galaxy is about 100,000 light-years wide, meaning the void is thousands of times larger than our entire galaxy. Based on the average density of galaxies in the universe, astronomers estimate that a region of space this size should normally contain around 2,000 galaxies. But when researchers surveyed the Boater's Void, they found something very different. Instead of thousands of galaxies, the region contains only around 60. The rest of the volume appears almost completely empty. When the Boater's Void was first identified in 1981 by astronomer Robert Kirshner and his colleagues, scientists initially wondered whether the discovery might simply be the result of incomplete observations. Perhaps telescopes had missed faint galaxies hidden within the region, or maybe the survey methods were not sensitive enough to detect smaller systems. Over time, however, more detailed surveys confirmed that the void was real. Follow-up observations using increasingly powerful telescopes continued to reveal the same picture: an enormous bubble of space containing far fewer galaxies than expected. The existence of such a large void does not completely contradict our models of cosmic structure formation, but it does push them toward their limits. Computer simulations of the universe show that voids naturally grow as matter flows into nearby filaments and clusters. As galaxies accumulate in dense regions, the surrounding areas gradually become emptier, but the size of the Boater's Void places it among the largest known supervoids in the nearby universe. Some astronomers have suggested that it may have formed from the merging of several smaller voids over time, gradually expanding as surrounding galaxies moved away into nearby filaments. Others have proposed that the region may have started with a particularly low density of matter shortly after the Big Bang, allowing gravity to evacuate it more efficiently as cosmic structures evolved. Despite these possible explanations, the Boater's Void remains an extreme example of how uneven the universe can become on large scales. Even though the cosmos appears uniform when viewed across billions of light-years, individual regions can still contain remarkable variations in matter distribution. Inside the Boater's Void, galaxies are scattered sparsely across immense distances, leaving vast volumes of space containing little more than dark matter, thin gas and faint radiation. If you were to travel through this region, you could journey hundreds of millions of light-years without encountering the dense galaxy clusters that are common elsewhere in the universe. It is a reminder that the cosmic web is not just a network of galaxies, but also a landscape of immense emptiness. The Boater's Void represents one of the quietest and most desolate regions known in the observable universe, a gigantic cosmic bubble where galaxies are rare and the darkness between them stretches for unimaginable distances. In 1965, two radio astronomers named Arno Penzias and Robert Wilson made one of the most important discoveries in modern cosmology. While working with a microwave antenna in New Jersey, they detected a faint background signal coming from every direction in the sky. At first, they thought it might be interference from their equipment, or even noise produced by the city around them. But after careful investigation, scientists realized that the signal was something far more remarkable. It was the cosmic microwave background, often shortened to CMB, the faint afterglow left behind by the Big Bang. This radiation fills the entire universe and provides a snapshot of what the cosmos looked like when it was only about 380,000 years old. At that early time, the universe had cooled enough for atoms to form, allowing light to travel freely through space for the first time. Ever since then, that ancient light has been stretching and cooling as the universe expands. Today it appears as extremely faint microwave radiation that is almost perfectly uniform across the sky. But when scientists map the CMB in great detail, they notice tiny variations in temperature, differences of only a few millionths of a degree. These fluctuations are incredibly important because they reveal the seeds of the cosmic structure we see today. Slightly warmer regions contained slightly more matter, which eventually grew into galaxies and clusters under the influence of gravity. Slightly cooler regions contained less matter and eventually became the vast voids between galaxy filaments. Because of this, cosmologists have studied the CMB with extraordinary precision, using satellites such as WMAP and the Planck Space Telescope. Their measurements have produced incredibly detailed maps of the early universe, showing patterns that match theoretical predictions remarkably well. But hidden within those maps is one region that stands out as particularly unusual. It is known as the CMB cold spot, a patch of sky where the temperature of the cosmic microwave background appears noticeably lower than expected. The cold spot lies in the direction of the constellation Eridanus and spans an enormous region of the sky, covering an area nearly 2 billion light-years across when projected into the distant universe. In CMB maps, it appears as a large circular region that is slightly colder than the surrounding radiation. On its own, a cold region in the CMB is not surprising. The early universe contained many tiny temperature fluctuations, and some of them appear slightly cooler than others. What makes the cold spot unusual is its size and depth. Statistically, fluctuations this large are not impossible, but they are somewhat unlikely according to the standard model of cosmology. Because of this, astronomers have spent years investigating possible explanations. One idea is that the cold spot might be caused by a supervoid, a massive region of space with far fewer galaxies than normal, located between us and the distant CMB radiation. As photons from the cosmic microwave background pass through such an underdense region, they lose a tiny amount of energy due to gravitational effects, making the region appear slightly cooler when observed from Earth. Astronomers have indeed identified a large void in roughly the same direction as the cold spot, but calculations suggest that it may not be large enough to fully account for the temperature difference that we observe. Another possibility is that the cold spot is simply a statistical fluctuation, an unusually large but still random feature produced by the natural variations in the early universe. If this explanation is correct, the cold spot would be rare, but not fundamentally mysterious. However, some researchers have explored more speculative ideas. One hypothesis suggests that the cold spot could be evidence of a collision between our universe and another universe in the distant past. According to certain models of cosmic inflation, our universe might be one of many bubble-like universes within a larger multiverse. If two such bubbles briefly touched during their formation, the interaction might leave an imprint in the cosmic microwave background. This idea is highly speculative and remains far from proven, but it demonstrates just how intriguing the cold spot appears to cosmologists. After decades of study, scientists still debate whether the cold spot is simply an unusual statistical feature or a sign of something more profound about the structure of the cosmos. Either way, it remains one of the most curious anomalies in our map of the early universe, a faint but persistent reminder that even the oldest light in existence can still hold unexpected surprises. Among the billions of stars scattered throughout our galaxy, most behave in ways that astronomers understand quite well. When scientists study a star, they often analyze its spectrum, the pattern of light that reveals which chemical elements are present in the star's atmosphere. Each element absorbs light at very specific wavelengths, creating a kind of fingerprint that can be detected by spectrographs attached to telescopes. By studying these spectral lines, astronomers can determine whether a star contains elements such as hydrogen, helium, iron, calcium, or dozens of other substances. In most cases, the results make perfect sense. Younger stars tend to contain heavier elements produced by earlier generations of stars, while older stars are usually composed mostly of hydrogen and helium. But occasionally, a star appears whose chemical fingerprint raises serious questions about how it could possibly exist. One of the most unusual examples is a star known as Przybylski's star, located roughly 410 light-years away in the southern constellation Centaurus. The star was first studied in detail during the early 1960s by Polish-Australian astronomer Antoni Przybylski, who noticed something deeply puzzling while examining its spectrum. Instead of showing the familiar mixture of stable elements typically found in stellar atmospheres, the star appeared to contain extremely rare and unusual elements, including short-lived radioactive elements such as technetium and promethium. Under normal circumstances, these elements should not survive for very long. Many radioactive isotopes decay quickly, sometimes in days, weeks, or years. Even the longest-lived isotopes generally last only a few million years before breaking down into more stable forms. Compared with the billions of years that stars typically exist, this means such elements should disappear relatively quickly. Yet astronomers have continued detecting traces of these unstable elements in Przybylski's star for more than 60 years. That observation alone raises a difficult question. If these elements decay so rapidly, how can they still be present in the star's atmosphere today? To explain this mystery, scientists have proposed several possible mechanisms that might continuously produce or replenish the unusual elements. One idea involves nuclear reactions occurring within the star itself. Certain types of stars, known as chemically peculiar stars, possess extremely strong magnetic fields that can influence how elements move through their atmospheres. In these stars, radiation pressure and magnetic effects can cause specific elements to accumulate in certain layers of the atmosphere, while others sink deeper below the surface. Przybylski's star is classified as an AP star, a type of chemically peculiar star known for its strong magnetic field and unusual chemical composition. Some researchers have suggested that interactions between the star's magnetic field and energetic particles might produce nuclear reactions capable of generating rare elements directly in the atmosphere. Another possibility is that decay chains from heavier elements could be responsible. For example, certain long-lived radioactive elements buried deeper within the star might slowly decay into shorter-lived isotopes that eventually appear in the outer layers where astronomers can detect them. This process could create the illusion that unstable elements are constantly present, even though they are being continually produced through decay. A more speculative explanation suggests that the star may contain extremely heavy elements, such as uranium or even super-heavy elements formed in earlier stellar explosions. If these heavy elements exist within the star, their decay processes could produce many of the unusual isotopes observed in its spectrum. However, confirming such a scenario is extremely difficult, because the signals detected in the star's light are faint and often overlap with other spectral features. Over the decades, astronomers have continued studying Przybylski's star with increasingly powerful instruments, hoping to better understand its unusual chemistry. Despite these efforts, the star remains one of the most chemically mysterious objects known in the Milky Way. Its spectrum appears almost like a cosmic laboratory, where rare elements emerge in ways that scientists still struggle to explain. While the mystery may eventually be resolved through improved observations and theoretical models, for now Przybylski's star stands as a reminder that even something as familiar as a star can still surprise us with properties that challenge our understanding of physics and stellar evolution. In October of 2017, astronomers scanning the sky for near-Earth objects detected something unusual moving rapidly through the inner solar system. The object was first observed by the Pan-STARRS, one telescope in Hawaii, a survey instrument designed to detect asteroids and comets that might pass close to Earth. At first, the discovery seemed routine. New objects are detected in our solar system all the time, and most turn out to be ordinary asteroids orbiting the Sun. But as astronomers began calculating the trajectory of this particular object, they noticed something extraordinary. The path of the object did not match the orbit of any typical solar system body. Instead of following the elliptical orbits that planets, asteroids, and comets normally follow around the Sun, this object was traveling on a hyperbolic trajectory. That meant it was not bound to the Sun at all. It had entered our solar system from interstellar space and would soon leave again, never to return. This made it the first known interstellar object ever detected passing through our solar system. The object was given the name Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. Its discovery immediately sparked enormous interest among astronomers because it offered a rare opportunity to study material that formed around another star system. As telescopes around the world turned toward the object, scientists began measuring its brightness, motion, and composition as carefully as possible before it disappeared back into deep space. One of the first things astronomers noticed was that Oumuamua's brightness changed dramatically as it rotated. The variations suggested that the object had an extremely unusual shape. Early estimates indicated that it might be long and narrow, possibly resembling a cigar-like form several hundred meters in length, but much thinner in width. Later studies suggested that it might instead be flat and disc-like, more like a pancake than a cigar. Either way, the object appeared far more elongated than most asteroids found in our solar system. This unusual geometry alone made it an intriguing mystery. As observations continued, astronomers encountered another puzzling feature. When comets travel close to the Sun, they usually release gas and dust as solar heat vaporizes ice on their surfaces. This process produces a visible cloud called a coma, along with a tail that streams away from the Sun. The escaping gas also acts like a tiny rocket engine, pushing the comet slightly and altering its motion. But when scientists observed Oumuamua, they could not detect any visible coma or tail at all. Despite this, careful measurements showed that the object was experiencing a small but measurable acceleration as it moved away from the Sun. Something appeared to be pushing it, yet telescopes could not detect the usual signs of outgassing that accompany comet activity. Several explanations have been proposed to solve this puzzle. One idea suggests that Oumuamua might be composed of exotic ices, such as hydrogen or nitrogen ice, which could evaporate without producing large amounts of visible dust. Another possibility is that the object contains frozen nitrogen, similar to the surface of Pluto, which might sublimate in sunlight and produce the observed acceleration while remaining difficult to detect. Some researchers have also suggested that the object might have been fragmented or reshaped by collisions in its original star system, giving it its unusual geometry. Because the object passed through the solar system so quickly, astronomers had only a short window of time to collect data before it became too distant to observe clearly. As a result, many aspects of Oumuamua remain uncertain. A small number of scientists have even proposed more speculative ideas, including the possibility that the object could be some form of artificial probe or technological debris from another civilization. However, most astronomers consider such explanations extremely unlikely and instead focus on natural scenarios involving unusual compositions or formation processes. Today, Oumuamua continues its journey through interstellar space, slowly fading from view as it travels farther from the Sun. Because it arrived unexpectedly and departed so quickly, we were only able to gather limited information about it. Future surveys may detect more interstellar visitors passing through our solar system, allowing scientists to study them in greater detail. But for now, Oumuamua remains a fascinating reminder that objects from distant star systems occasionally wander into our cosmic neighborhood, carrying with them clues about places we may never directly observe. In June of 2018, astronomers monitoring the night sky noticed something unusual appearing in a distant galaxy. The event was first detected by the Atlas survey, a system of telescopes designed to search for sudden changes in brightness across the sky. At first glance, the object seemed like it might be a normal supernova, the explosive death of a massive star. But almost immediately, scientists realized that this event was behaving very differently from anything they had seen before. The explosion brightened with incredible speed, reaching its peak brightness in just a matter of days. Most supernovae take weeks to gradually brighten and then slowly fade over the course of several months. This event, however, appeared suddenly, became extremely luminous, and then began fading again much faster than expected. Because of its catalogue name, AT2018 Cow, astronomers quickly began referring to the object simply as the Cow. Despite the playful nickname, the phenomenon itself was anything but ordinary. The explosion was estimated to be 10 to 100 times brighter than a typical supernova, yet it rose and faded on a time scale that seemed far too fast for such an energetic event. Observations showed that the light emitted by the object was also unusually blue, indicating extremely high temperatures. As telescopes across the world turned toward the event, astronomers gathered data across many wavelengths, including optical light, radio waves, and X-rays. The results only deepened the mystery. Unlike most supernovae, which are produced when the outer layers of a star are blasted outward into space, AT2018 Cow appeared to reveal something happening deep inside the explosion itself. Some observations suggested that astronomers might be seeing the central engine of the explosion directly, possibly a newly formed black hole or neutron star powering the event from within. This idea was particularly intriguing because the dense material ejected during a normal supernova usually hides the inner core from view. Yet in this case, the explosion seemed thin enough that radiation from the central region could escape. The unusual properties of AT2018 COW soon led scientists to realize that it might represent an entirely new category of cosmic event. Over the next few years, astronomers discovered several similar explosions, now referred to as fast blue optical transients, often shortened to FBOTs. These events share several distinctive characteristics. They appear suddenly and brighten extremely quickly, often reaching peak brightness within just a few days. They also produce very hot, blue light and then fade far more rapidly than typical supernovae. The energy released during these events is enormous, yet the physical mechanism driving them remains uncertain. One possible explanation is that these explosions occur when a massive star collapses directly into a black hole producing powerful jets of energy that blast outward through the surrounding material. Another idea suggests that they may be connected to the birth of rapidly spinning neutron stars, sometimes called magnetars, which release huge amounts of energy through intense magnetic fields. There is also evidence that some FBOTs interact with dense shells of gas surrounding the star, which could amplify the brightness of the explosion and alter how the light evolves over time. Despite these theories, no single explanation has yet fully accounted for all of the observations associated with AT2018 Cow and similar events. What makes these explosions especially intriguing is how quickly they appear and disappear. Because they evolve so rapidly, astronomers must react almost immediately when one is detected, coordinating telescopes around the world to observe the event before it fades from view. Each new detection provides additional clues about the extreme physics taking place in these cosmic explosions. The discovery of AT2018 Cow forced astronomers to recognize that the universe still contains categories of phenomena that had never been clearly observed before. It also demonstrated how modern sky surveys, which continuously monitor huge portions of the sky, are revealing transient events that would have gone unnoticed in the past. As more of these fast blue transients are discovered, scientists hope to build a clearer picture of the processes that create them. For now, they remain one of the newest and most energetic mysteries in modern astrophysics, brief flashes of extraordinary brightness that challenge our understanding of how stars live and die. For most of the history of astronomy, determining the age of stars has been one of the key ways scientists try to understand the history of the universe. By studying a star's brightness, temperature, and chemical composition, astronomers can estimate how long it has been burning its nuclear fuel. These measurements are then compared with models of stellar evolution, which describe how stars change over billions of years as they fuse hydrogen into heavier elements. In general, these models work remarkably well. They allow scientists to estimate the ages of star clusters, reconstruct the formation history of galaxies, and even place limits on the age of the universe itself. According to our best current measurements, the universe is about 13.8 billion years old. This estimate comes from several independent observations, including measurements of the cosmic microwave background, the expansion of the universe, and the evolution of galaxies over cosmic time. Because the universe has a finite age, no star should be older than the universe that produced it. Yet in the early 2000s, astronomers studying a nearby star encountered a puzzling result that seemed to challenge this fundamental assumption. The star, known as HD 140283, quickly gained the nickname the Methuselah star, after the biblical figure said to have lived for nearly 1,000 years. Located about 190 light-years from Earth in the constellation Libra, this star is relatively close in astronomical terms, making it an excellent target for precise measurements. It is a type of star known as a subgiant, meaning it has already exhausted much of the hydrogen in its core and has begun evolving away from the main stage of stellar life. When astronomers analyzed the star's properties in detail, they discovered that it contains extremely low amounts of heavy elements, indicating that it formed very early in the history of the universe, at a time when only the simplest elements existed. That alone was not surprising. Many ancient stars formed shortly after the first generations of stars began enriching the universe with heavier elements. What surprised scientists was the estimated age of the star. Early calculations suggested that HD 140283 might be around 14.5 billion years old, which appeared to make it older than the universe itself. Naturally, this created considerable excitement and confusion among astronomers. If the measurement were correct, It would imply that either the age of the universe had been underestimated, or that our models of stellar evolution were missing something important. Over time, astronomers revisited the data using increasingly precise instruments, including observations from the Hubble Space Telescope. By refining the distance to the star and improving the models used to estimate its age, scientists were able to reduce the uncertainty in the calculations. The updated estimates suggested that the star is likely around 13.5 billion years old, with a margin of error of several hundred million years. This places its age just slightly younger than the universe itself, though still incredibly ancient. In other words, the Methuselah star is not actually older than the universe, but it formed very close to the beginning of cosmic history. Even so, the star remains one of the oldest known stars in our galactic neighborhood, offering astronomers a rare glimpse into the earliest generations of stellar formation. Studying stars like HD 140283 helps scientists understand what the universe was like shortly after the Big Bang, when the first stars were beginning to form from clouds of hydrogen and helium. These ancient stars act almost like cosmic fossils, preserving information about the chemical conditions that existed billions of years ago. The story of the Methuselah star also highlights an important aspect of science. Sometimes discoveries appear to contradict our understanding of the universe, but with better observations and improved models, those apparent contradictions often reveal deeper insights into how nature truly works. The universe is vast, complex, and still full of mysteries waiting to be understood. From unexplained radio signals and strangely dimming stars to enormous cosmic structures and ancient stellar relics, the discoveries we've explored in this journey show just how much there is still to learn about the cosmos. And as telescopes become more powerful and our observations more precise, it's very likely that even stranger discoveries are still waiting quietly in the darkness of space, ready to surprise the next generation of astronomers.